Hello and welcome back to Fourier Transform, the video series where we talk a lot about a special integral transformation and what we can do with it. And indeed, in today's part 26, we will talk about the so-called Riemann-Lebesgue Lemma in the continuous version. You might remember that we have already discussed it for the Fourier Series, and now we will do it for the Fourier Transform. It will simply tell us more about the codomain of the operator given by the Fourier Transform. In particular, we will look at the limits of the functions that come out. And what this actually means I will tell you soon, because first I want to thank all the nice people who support this channel on Steady, here on YouTube or via other means. And you should know, as a member on Steady or Patreon, you can download a lot of additional material for all the videos. For example, it's quite helpful to have the corresponding PDF version of this video in front of you. And with that said, let's get started, and first we should recall the definition of the Fourier transform on L1. And you already know, this is a well-defined operator that we can shorten by the head symbol. And then as already mentioned, the input is given by L1 functions and the output lies in the continuous functions. More precisely, we have already shown that these continuous functions are also bounded. So please note, the L1 functions on the left don't have to be bounded at all, but what comes out after the Fourier transform is definitely bounded. And moreover, if we call the input f, then the output is called f hat. And usually what we do is to call the variable on the left x and on the right hand side p. That's why we have f hat of p, and you already know it's given by this nice formula. And now what we will do today is to specify this output space even more. In fact, the Riemann-Lebesgue lemma will tell us that all the functions that can come out here have well-defined limits for p to infinity. Moreover, this limit is always equal to 0. Therefore, we are allowed to change this codomain to C with index 0. And this simply stands for the space of continuous functions that vanish at infinity. And the precise definition of that we can now formulate in the so-called Riemann-Lebesgue lemma. And I say that this is the continuous version because in part 22 we already had the Riemann-Lebesgue lemma for Fourier series. The statement is actually the same, but there it was about sequences in the output space instead of continuous functions. And now the statement here is quite short. No matter which integrable function f we choose, we always get out a C0 function. This means if you look at the value f hat of p and you increase p more and more in the standard norm, then this value will go to 0. So you can just write that the limit here for p to infinity is equal to 0. So we have two claims here. First, this limit always exists, and second, it's given by 0. And in the case that you don't like this short limit description here, you can also go to sequences. So you just take any sequence pk in Rn, and this one now should be unbounded, and even more, we want that the standard norm of this pk goes to the improper value infinity. So this is a sequence of real numbers that is divergent to infinity. And now the result is that the other sequence of complex numbers, given by the values, is a convergent sequence with limit 0. And that's it. This is the full meaning of the limit description here on the left hand side. So this is the whole Riemann-Lebesgue lemma, and you can remember it by just saying that this integral here goes to 0 whenever p goes to infinity. And for the rest of the video, we will try to prove it. In order to do that in an efficient way, we will first look at a simple case for our function f. Namely, we will just look at so-called CC functions, which are compactly supported continuous functions. This is even more than saying that we vanish at infinity, because what we have is that everything interesting for the function happens inside a compact set. This means for every given CC function f, we can find a positive radius r, such that outside a ball with radius r, this function completely vanishes. And this also tells us that the support of this function lies in the closure of this open ball. A typical picture of such a nice function is something like that, where we have a bump in the middle and outside of a bounded set we are equal to 0. And in fact, we can make these functions even nicer. Instead of continuous functions, we could consider smooth functions. If we want that all the partial derivatives of f exist, we would add an infinity symbol to the c. So in the end, what we consider here are c infinity functions with compact support. And this also implies that any partial derivative of such an f is a c infinity function again. In addition, we can even choose the same radius r again to cover the whole support. Hence, our integral from the Fourier transform actually only goes over a compact set. So maybe more concretely, this would be the definition of the Fourier transform of the new function given by the partial derivative, and instead of Rn, we can just integrate over BR0. And this is a big advantage in this case, because we only have to care about a bounded set. And in fact, it does not matter how large we choose the radius, we can even increase it by 1. The point is that we can work inside such a ball. And now you might already guess what we can do here is to use integration by parts to shift this partial derivative to the left. If you don't know the integration by parts formula in n dimensions, it's not a problem at all because I have a whole video about it. But I can already tell you, if you watched the video, you will see that the whole formula is completely analogous to the one-dimensional case. This means we first get one part over the boundary and then minus the integral where the roles are flipped. So the formula looks like this, and the boundary of the ball is clearly the sphere with the given radius. And that's the reason I don't have to write down the details of this part, because we already know that the function f and all its derivative vanish on this sphere. So clearly everything is 0 there, so we don't have to care about that at all. So since the boundary terms vanish here, we get a really nice result for the Fourier transformation of the partial derivative. Namely, we have the minus sign, and then we have to calculate the partial derivative of the exponential function. And there you actually just have to know that the standard inner product is given by the sum of the products. In other words, we just have an inner derivative where pj comes to the front together with minus I. And obviously the outer derivative still has the same exponential function. And with that we have it. Now we can just pull out this factor, and what remains is just the Fourier transform of the original function f. So we get ipj times f hat of p. In fact, this is a really important result for the Fourier transform. It tells you that the partial derivative with respect to xj translates to I times pj. So you can just remember the Fourier transform translates differentiation into multiplication. And this nice formula is something we can use to estimate what happens when pj goes to infinity. And of course pj could also go to minus infinity, so we can just look at the absolute value here. And now by using the formula from above, we know that this one is the absolute value of the Fourier transform of the partial derivative. So this is already quite nice, and now you might already guess the next thing we want to do is to pull in the absolute value into the integral. This is what we call the triangle inequality for the integral, and then you see the exponential function will just vanish with the value 1. So what remains is just the absolute value of the partial derivative of f inside, and there we know the whole integral has a well-defined value. So maybe let's abbreviate this number by Cj. We don't care about the value, it's just important that this number does not depend on p. And at this point you might already recognize what we wanted to prove from the beginning, because if pj increases more and more, we are still bounded by cj. Hence the other part in the product, f hat of p, has to decrease even more, so it has to go to 0. And that's already it, because we have the result for every possible index j, we are done. For example, we could state it like that: if the standard norm of p goes to infinity, then at least one component pj has to go to infinity in the absolute value. And exactly for this given j, we can use the estimate from above. And then we know this simply has to go to 0. And there we have it, case 1 is done. Compactly supported smooth functions are not a problem for us. And now the second case is just the general case. We want to show it for every other L1 function. And now it turns out that this is not a problem at all for us, because we can just use an approximation with the functions from above. For this approximation I also have a whole video where I actually prove that this one always works. Therefore, for any given small number epsilon, we can find a function g in CC infinity that is close to f. And obviously the distance between these two functions should be measured in the L1 norm. So what we want is that f minus g in the L1 norm is less than epsilon. In other words, the distance is simply measured with respect to the integral. So maybe to make it clear here, the L1 norm is simply given by the whole integral over Rn of the absolute value for the difference of the two functions. And because we have that, we can also pull out the absolute value and add the exponential function inside to get the Fourier transform again. And this should not surprise you, because you already know that in the end we want to talk about f hat. And now you see we simply have the difference of f hat and g hat. And moreover, we already know, no matter what point p we choose, we already know that this difference is less than epsilon. However, we should never forget that we talk about complex values here, so when we want to talk about distances, we always need the absolute value. So for example, we know that these two complex numbers are closer than epsilon, which means that the absolute values cannot differ much. More precisely, the inequality tells us that f hat of p lies in an open epsilon neighborhood around g hat of p. Therefore here I can just write the open interval g hat of p in the absolute value minus epsilon to the same number plus epsilon. So this is the open interval we have here, and now we can use the result from above, which tells us that g hat of p goes to 0 whenever p goes to infinity. So there it comes in. This is the advantage that we already know what happens for the CC infinity functions. And then what we get here for f hat is a really tasteful sandwich theorem. So no matter what we do, the limit of f hat cannot escape this epsilon neighborhood. However, since we don't know if the limit exists, we can look at something that definitely exists, for example the limit superior. And now since g hat of p goes to 0, we know that the limit superior lies between minus epsilon and plus epsilon. Indeed, we have to include the boundary, but this does not change much. Moreover, we can also look at the limit inferior, and clearly the sandwich theorem holds there as well. So also there we get out our interval, and actually for both things we know we cannot be negative, so we actually are in the interval from 0 to epsilon. But definitely the crucial thing you should see here is that this result holds regardless of the epsilon chosen at the outset. Hence we can make the limit superior and the limit inferior as small as we want. Therefore the only possibility is that they are both equal to 0. And this immediately implies that the whole limit exists and is also equal to 0. And that's already it. This shows the whole Riemann-Lebesgue Lemma. You see, it tells us much more about the image of the Fourier transform, and what we can do with this information I will tell you in the next videos. So I really hope I meet you there again, and have a nice day. Bye bye.